Hey, everybody. Good morning. Good afternoon. Thank you for joining us at another of our Tech Talks. If you are new to Tech Talks and this is your first one, or if you've been with us before, welcome. And thank you for taking the time to come hang out with us today. My name is Mary Benyon, and I'll be moderating today's presentation. But before we get started, I just want to give you an idea of how you can get a hold of us. Jake, if you have a minute, you can share the deck. So let me throw a slide up for you. There we go. Here you can find us if you happen to be listening to something that compels you, tweet at us at ARM Software Dev, and also tag DarwinAI. We have a developers YouTube channel. We'll be posting this to after the presentation. You can find upcoming Tech Talks at that link. Also, if you would be so kind to fill out our survey after, we really want to hear back from everybody to understand how we're doing, what the topics are, and if there's something that we're not bringing to you, suggestions. We really want to make these as informative and interesting to you guys as possible. And we are giving away Arduino Nano 33 BLE boards for your taking the time to help us with the survey. Next slide, Jake. This is the upcoming Tech Talks that we have over the next few weeks. So please make sure that you get registered for those. I think all of them are great. I can never decide which one I'm more excited about because they're all so different and super cool. So go to the website where you can register. And then finally, let's go to the next slide and get going on the presentation. I'm really happy to introduce you to DarwinAI. I've always been very impressed with them, especially about a year ago. They're the ones that brought us COVIDNet, that they released open source to help the world in its fight against COVID. And this is just one of the things that I've seen that they're involved with over this past year, and they're involved in so many cool things. So I think you're going to really enjoy listening to these guys. So we've got Alex Wong. He's the co-founder and chief scientist from DarwinAI, and then Jake Walker, who's the senior product manager at DarwinAI. So Jake, are you ready? Are we ready to do this? How are things where you are?
Yes, thanks, Mary. I'm ready. I'm ready to go, and excited to show everyone what's happening.
Awesome. All right, let's do it. Please, during the presentation, pop your questions in the Q&A. We'll be answering questions towards the end, so feel free to put them in there, and we'll get to them at the end. So Jake, it's all you.
Okay. Thanks a lot, Mary. And thanks everyone for joining today's Tech Talk. And also thanks ARM for hosting. It's a really cool opportunity for us to show what we have in the works. So today we've split content into three main sections. So we'll talk to you briefly about us, so who are we, DarwinAI? We'll talk about a case study, and then we'll show you our solution for visual defect detection. So first, DarwinAI. Who are we and what are we doing? At DarwinAI, we're a small and growing team of more than 30 team members. 65% of us have a PhD or master's degree in the field of AI. It's really incredible to be surrounded by so many intelligent people, and it's super humbling to be in conversations where we're constantly learning and challenging ourselves. To date, we have more than 9 million invested, more than 30 patents, more than 600 publications, and more than 20 research awards. Our IP is proven and doesn't stop growing as a research team led by Alex. Doesn't stop innovating and challenging what's possible every day. We're not fresh out of the gate. Our team has much experience with large multinational enterprises such as Audi, Honeywell, Lockheed Martin, and many others. So this is our new tagline. If you haven't been to our website, go check it out, because we just launched our new website a few days ago. There's a lot to see there, and just kind of gives you some more context as to what we're doing. But In general, we build trustworthy AI that scales, and we empower leading enterprises to solve their most critical challenges. We are building explainable AI products for manufacturers and innovating in a way that matters to create positive progress for enterprises worldwide. So enough of that. Let's get into the case study. That's kind of who we are in a nutshell. And as promised, by the title of the talk, I'll talk to you a case study of how deep learning can impact manufacturing. So the customer that this case study is centered around is a global aerospace and defense manufacturer. They're headquartered in the United States. They have more than 50 plants, more than 10,000 employees, and they've been in business for more than 50 years. So they are a very, very well-established company. The problem. So what is their problem? So when manufacturing advanced motion control products for mission critical applications in the aerospace industry, every component must meet rigorous quality standards. PCBs are no exception and super high up on that list. For example, NASA's acceptance standards require over 20 types of surface defects to be distinguished and reconciled. This manufacturer was experienced several difficulties with their existing inspection process when building their PCB boards, such as high lead time. More than 40% of defects found during inspection could have been detected 2 days earlier during PCB soldering. They experienced high scrap rates. The entire batches are scrapped when defects are found after the fact, wasting thousands of dollars in raw materials. And there's also penalties too. So manufacturing companies delays can incur significant penalties from customers if they don't get those products to their customers in time. So hopefully that helps orient on why this problem was impactful to this customer. Now I'd just like to walk you through the manufacturing process, iterate, and then tell you how AI can be introduced to improve things. Here's a version of a standard process for a manufacturing facility where raw materials are used to build a product in several stages, followed by a full quality inspection. If there are issues of the final product, then the assembled product is either fully scrapped, or if it's not reworkable, or time is taken to rework as needed, followed by another final inspection. The other option, which can be more resource heavy but reduces rework time and other uncertainties, is to have quality inspection done after each of the processes, preventing defect flow out at each micro level. If parts need to be scrapped, then the cost of scrapping is less, since less components and parts have been built into the assemblies at those stages. And if defects are found and are reworkable, then the parts are sent back to the process where the issues can be fixed. This takes time and delays the delivery of the part to the next process, and because of that, the end customer. The reason quality inspection needs to be done in separate processes from processes where assembly is done is either because the person doing the building doesn't have time to do the quality inspection, or special tools are required to provide definitive results. In the case of this customer, the through holes on the multi-layer PCBs they built were very difficult to inspect by eye and therefore needed microscopes. And because even with a microscope, defects are hard to see, specialized subject matter experts are required to find those defects. But even then, because they're so difficult and because of inevitable human error, defects still slip through. This breeds opportunity for integrating intelligent defect inspection to supplement the work of the builder, meaning the member installing the parts on the assembly can finish their work, then review the results on screen. If there are defects, then the part doesn't need to go to another process just to find the same defect, just to come back for rework. This all takes time. So you do the work, you automatically inspect, you fix if required with high confidence from a deep learning system trained to find those defects with high accuracy. This ultimately improves the productivity of the entire manufacturing process and significantly increases the chance of catching every single defect as it happens. You can even take it one step further and implement deep learning inspection on the raw materials used in each of the assembly processes. So this allows manufacturers to find defects on parts, meaning once they're assembled, you know that there are no issues beforehand. They can then use the inspection reports to hold suppliers accountable to their parts, recuperating costs and improving negotiation power with actual evidence. There's a lot of benefits to it. Ultimately, the cost to the manufacturer of scrapping raw materials is significantly less than it is of scrapping a full assembly if defects aren't found until after assemblies are complete, sometimes 10 times more expensive. So hopefully that provides some magnitude there. And hopefully that explains why finding defects is so important to develop an innovative solution for. Now I'm going to transition to how we're approaching our solution, which is visual defect detection for manufacturing environments. So first, a problem statement. Manufacturers' existing inspection processes, the existing inspection process isn't optimal, and it's resulting in unnecessary defect-related cost, like scrap or productivity. The second problem in general, thinking about this from the perspective of it being a problem that's hard to solve with existing technology available, there are also limited ways to show quick wins through innovation. This is more of a problem of how to deploy and sell within your organization. But why AI? Simply put, because existing visual inspection solutions just aren't good enough. Using AI brings in capabilities like adaptability, time to value, and continuous learning. A very interesting point in this realm, humans are only somewhere between 70 to 90% capable of detecting defects by eye. You may be thinking, well, wow, that's a really big range. Why? Well, it just depends on the complexity of the inspection. And why is it not 100%? Simply put, humans experience fatigue, AI does not. Missed defects lead to flowout, which can be very bad for the business. Recalls, penalties, dissatisfied customers, negative brand trust impact, the list goes on. Manual inspection is just not sufficient to achieve optimized output quality of manufacturing products. AI systems are self-sustainable over time. They just get better the more data they have. And with a well-built enterprise solution, scalability across an organization is possible to achieve optimized ROI. We're not focused on point solutions, but an enterprise manageable solution. Deep learning is optimal for defect detection. It just is. It's exceptional at recognizing when samples deviate from expectation. Enormous value can be unlocked in a wide range of contexts, and it's visual. This means that it can be used for anything that can be seen with a camera. PCB boards, automotive parts and assemblies, hard to see welds. Again, the list goes on. So our offering, what we have is an end-to-end platform solution that is tailored to be used by engineers and subject matter experts within manufacturing environments. We also have an API solution to allow for customization and to harness our unique capabilities, such as our advanced XAI technology. This can be used by custom fabricators and system integrators looking to build their own hardware-software solutions. So now I'd like to turn it over to Alex, and Alex is just going to do a little bit of a talk on our generative synthesis solution.
Thank you, Jake. So just want to go a little deeper tech dive into our DarwinAI generative synthesis solution in terms of helping you really get a much better appreciation as well as trustworthiness in the AI solutions deployed. So in the case that Jake just mentioned, where underlying the goal is to identify defects both at the assembly as well as in the actual raw materials itself. One of the key components of the DarwinAI generative synthesis technology that becomes especially important is what we call quantitative explainability. So quantitative XAI, because quantitative XAI enables you to get additional insights to allow for high precision and reliability in your overall system. It provides you the ability to do more with less in terms of your training data, as well as improve, get really localized explainability that show the root causes directly related with proper context. So with quantitative explainability that's unique to DarwinAI's underlying technology, it not only provides a rough explanation of what might be happening, but it actually gives you a very detailed quantitative picture into the actual decision-making process of the AI solutions that you build, as well as provide quantitative justification. So if we go on to the next slide, how does this compare with some of the more very popular open source alternatives in terms of explainability, such as Lime, SHAP, expected gradients, and so on and so forth? And so what's unique about, I guess, the Jensen's quantitative explainability, which we call GS Inquire, is that it provides a much more quantitative explanation compared to some of the other approaches. So for example, an example of Lime, which is a local proxy-based approach, what they try to do is they try to create a local model to try to explain local behavior, but it doesn't get the full sense of the entire scope of the problem at hand. And this could be particularly limiting when it applies to particular scenarios, such as in the manufacturing case, where knowing the full picture becomes very important for identifying and really explaining the decision-making processes of AI models in a quantitative and trustworthy manner. And so what else does this quantitative explainability from DarwinAI enable? It also enables a much broader task agnostic explainability. So with approaches like Lime, SHAP, and so on and so forth, it's largely centered around classification. So you go back to the previous slide. Whereas with the Jensen quantitative explainability through GS Inquire, it allows you to apply a variety of different tasks, which are very important for manufacturing, ranging from classification to segmentation to object detection. It also ensures that the explainability, the explanations that are provided are in fact highly relevant and directly reflect the decision-making process of the actual AI model itself. Whereas with approaches such as Lime, SHAP, and so on and so forth, it really just gives you a general picture as what might be important to look at. So it imparts a lot of human interpretability in order to actually interpret the explanations themselves. And so with what we're providing, we're able to provide a much higher confidence in terms of the critical factors that is identified through our explainability linked to the actual decision-making process itself. So for example, in this case, being able to localize defects both in raw materials as well as in this during assembly to really explain why your AI solution has flagged, let's say, a particular part as being defective, and it requires much less effort to incorporate directly into your models as well as incorporate into your overall workflow. And so if you go into this slide, what do we mean by quantitative explainability? And so here what you see is quantitative explainability in action in a more general case. So here is a more of an image classification problem on natural images. And what you see is that instead of providing what is usually called a saliency map or a heat map to give you kind of a rough sense into what might be leading to the decision, here with the Jensen quantitative explainability, we're able to surface directly the exact critical factor that led to the decision itself, and we can confirm it based on quantitative justification. So looking at the top left example, we have a warplane, and what the Jensen XAI is able to tell you exactly is that this particular region associated with the front, the nose of the actual warplane, was the most critical factor that did in fact lead to decision. And it led to decision of a warplane with 98.7% certainty. Not only that, it provides a quantitative justification that in any kind of alternative case, that it would have thought it was a parachute with 23.5% certainty. So you have not only the explanation itself that's linked directly to the decision-making process, but also the justification around it, which is very important, especially for inspectors in leveraging this type of manufacturing defect detection AI. So we go next. So here's an example. And so how does it compare with some of the other approaches? So as I just mentioned before with the Jensen quantitative explainability, you're able to get quantitative these specific critical factors that did result in the actual decision. Whereas here, comparing to Lime and SHAP, you have pretty much these heat maps that are much less localized around what is important. You can't actually link it directly to the quantitative decision-making process. And in many cases, especially looking at the top right, which is the Lime example, it's very difficult to interpret the actual explanation itself. And so from a real world manufacturing scenario, having this quantitative explainability makes it much easier for inspectors as well as designers to really understand. And so we go next. So what does this actually enable? So I'm going to turn it back to Jake to talk more about how this enables inference at the edge.
Thanks, Alex. Yeah, so hopefully that provided some good context with like what's really deep rooted in our solution. And now I'd like to show you our solution. Here's an example of the inspection display that would be in a quality checking process. So after the camera's all set up, model is optimized for use on edge hardware such as ARM and is communicating with the camera. Images are taken of the part being inspected. It's displaying to the subject matter expert with a mask overlay showing the inference result. If there's a defect, it will show what the defect is and where it is on the part. In this example, there's a disconnected component wire found. Some critical information shown is inference speed, model accuracy percentage, classification confidence percentage, false positive and false negative rates. Those are sometimes referred to as overkill and escape rates, depending on your perspective. The next step here is then for the subject matter expert in the process to provide feedback on that inference result. So 1, is the classification correct? And 2, is the localization correct? This information is then used as ammunition to retrain the model, ensuring model confidence is improved over time. This is a powerful component that provides transparency to humans and confidence that humans are involved in the performance of the deep learning, as opposed to it just being a black box. Furthermore, all data can be stored on a server for access by several stakeholders for several purposes, such as procurement teams pulling defect data to negotiate with suppliers, HR teams to analyze productivity versus the defect rates at different stations or factories, and planning groups who design manufacturing processes to identify broader issues in their production workflows based on where defects are occurring, develop higher level countermeasures accordingly, using all of our data because it's accessible. And that's the power of not just having an inference solution that provides defect detection, but utilizing all of that data for further use down the line for other stakeholders. So there's 2 main components here of how our system works. The first at the edge. So a camera provides an image to our image analysis application, which then runs the image through an edge optimized model to perform inference and utilize our XAI. Send that image with the result feedback to an MES or another system used to handle intra-plant communications to get to the server or cloud. Going here also allows for communication with any required network connected PLCs for control of factory devices such as conveyors. This leads us to the second component, which is the Darwin SDK. This can be either in the cloud or on premises, and it entirely depends on the customer's security requirements or general comfort with working in cloud environments. In general, a lot of the customers we work with have really high security requirements, so require on-prem solutions. We can work with both. Here is where all the data is retained, but also where the model training happens. The assumption that we're operating under right now is that for traceability and control reasons, it would be more desirable to pull an optimized model to a factory device as opposed to pushing it. And this would allow for manufacturing engineers to be in complete control of exactly what model is on an edge device in the case where there are multiple in their facility. So Alex, I'd just like to kind of pipe you back in here and just talk about how using ARM hardware can be beneficial.
Happy to. Thank you, Jay. So just want to kind of really go in detail how using ARM, processors have really helped us accelerate inference speed on the edge. And so what we did was we created in this case, a dedicated acoustic, or in this case, visual as well as types of models for identifying defects and problems. And so with this particular case, what you could see is that running on ARM processors, as well as using DarwinAI's GenSynth technology, where we leverage explainability to be able to automatically create more powerful yet greatly more efficient neural networks, what we're able to do was create neural networks that had a 10x speed up on the ARM processor compared to a standard solution. And we're able to do this for a number of different cases under different situations. And that's where the ability to combine DarwinAI's GenSynth technology and getting it really optimized for the ARM processors really enable manufacturing defect inspection at the edge. So back to you, Jake.
Thanks, Alex. So I just want to I want to take a quick step back for a second. Now that we've talked about inference, we've talked about setup. I'd like to highlight a really important point here about the fact that data labeling is massively important for any application, even more important in a manufacturing environment. Garbage in, garbage out. So a really kind of neat little quote here: if only 9 out of 10 images are labeled properly, then a perfect model is only going to be 90% accurate. Bad data will just result in poor performance of a perfect model. So we enable customers to achieve optimized data preparation and labeling in a very simplistic way. So here's a generic workflow of how that problem can be solved. You use production level data. This is important because lab POC data can be good, but won't be as good as production data or as representative of it. You get a collection of data that's representative of the use case. Then you enable subject matter experts to label images. They're the most well-equipped to say on this image, yes, there's a defect, because that's their job. They are the subject matter experts in that part, in that use case. But there's an ambiguity in that statement. So like, what if you have 6 subject matter experts? They're all in rotating shifts, or they're not all in the same place at one time. 1 volunteers to do all the labeling. And what if only 3 of the other SMEs agree with how that SME would label the image and the other 2 don't? So what we do is enable collaborative labeling. Each subject matter expert plays a part in labeling, and they can all see how each other have labeled images. And ultimately, that drives consensus, which is key to success and how a model can be best utilized. That gets you to the point where all the subject matter experts agree, yes, that is a defect and that is not a defect. Of course, that consensus is then retained with the images for future access and traceability. And now we can train the model. You can optimize it for target edge hardware, and then you can install it on the edge hardware. Ultimately, without that consensus on labeling, the likelihood that a perfectly trained model providing an inference result that would be agreed to by any one of the 6 SMEs is lessened. And before we kind of wrap things up and we kind of transition over to a Q&A period, I'll leave you with an overview of what our product platform looks like. Inference at the edge is only really a part of a successful enterprise solution. So there's also user feedback to enable continuous model improvement, as we talked about, a defect catalog, so you can see a representation of all the defects possible over time, defect tagging collaboration, as discussed earlier, image labeling tools to make it really, really easy to label images, inference feedback, as discussed, a system for managing your models at the edge. As time goes on, you'll have multiple models with potentially multiple inspection processes. You'll need a way to manage all of that so it doesn't get messy. A/B testing, so you can validate from 2 different models which one would provide the optimal inference result. And a library to manage all of the models developed over time for not just one process, but all the processes within a facility as you scale with our enterprise solution. So that's all I have. In the time that we have here, I'd like to just thank everyone, and I'm gonna check to see if we have some questions.
Yeah, hey, thanks Jake and Alex, that was awesome. So please, if you have any burning questions or things that you are curious about how this process works, please pop them in the Q&A box. And let's get to a question. So what environments can you work in?
Yeah, sure. So I think this really fits into what I said earlier about this being a visual application. So that really essentially means if you can take a picture of it, we can work with it. Surface, like plain surfaces on the side of a painted car, for example, PCB boards, finished welds with like put two parts together and put a weld bead down, and you can take an image of it and say, yes, that's good or that's not, based on training it. So that's kind of where we fit. I'm open to conversations with anybody if they've got a unique application that could fit into this visual problem. Then I'm happy to talk.
Yeah, it seems very flexible. The tool can be adapted to many environments, I would think.
That's the goal.
Yeah, and along those lines, we have a question from Ken. So, and I actually had a question myself that is the same question. So good job, Ken, that you and I think alike. How many SME validated images were required before going live with the PCB application? And the way I phrased it is, how long does good labeling take? So you described your collaborative process. What is that? I guess it's very subjective to the use case, but generally, what have you seen for, from the time you get the data, then the SMEs label it, and then you've got like a really good accurate model?
Time to value. We've got a model that we work through, and when we engage with customers, it can take anywhere from 1 week to 4 weeks. It just really depends on the use case.
Yeah.
It depends on the complexity of the image. And it depends on the customer's willingness to really kind of hit the ground running. Hopefully that answers the question. It is subjective to the use case.
Yeah, it sounds like there's a lot of factors that go into that, but it sounds pretty straightforward as far as how many images you want to collect and how good the data is, like you say, if you have a collection of SMEs, it probably takes longer. If you have one SME and they're like, yeah, this is it, boom, they're happy. So
exactly. If you've got a targeted process that's really handled by 1 or 2 people, it goes a lot quicker because
for sure,
collaboration between those 2 people is a lot easier to do. Whereas if you've got multiple shifts across multiple processes where you're trying to label images that have been collected from that place, it can take longer.
Yeah, for sure. Okay, let's see. There's another question. So how does GenSynth create a differentiation from the other model building platforms that are on the market? So essentially, what's your differentiator?
Oh, that's actually really interesting. I had a slide in here, but I took it out due to time. So I'm just going to shift. I'm going to bring it up, and I'm going to ask Alex to actually talk through it.
Sure. So happy to. So one of our key differentiators is the ability to kind of really streamline the typical MLOps pipeline to make it much more efficient and much more effective at creating very trustworthy AI solutions. So if you take a look at the typical model development process, where a lot of it is, while there's a lot of tools available to enable it, it's still a very manual and iterative process where you have to define your operational targets, collect your data, design your model prototype. So that's like the first step. But then you have to go through the, the pains of training the model, going through all the hyperparameters for your models, really kind of guesswork involved in creating even a starting model as you iterate through it. Then you validate your performance, then you try to deploy it. Then in most cases, you have to go back to each of the individual steps earlier on because you might find out I don't have enough data, or the initial model I set up is not so great. It doesn't meet my hardware requirements. It doesn't meet my accuracy requirements. So while the tools are available, it gets really cumbersome. And typically more than 50% of the development time is spent pretty much pursuing both a balance of accuracy as well as target operational targets, be it speed, size, accuracy, and so on and so forth, through this manual iterative process. right? So for me, it's often what I often call it is it's like throwing dice and hopefully you land on the right dice at the right time. Whereas with the general synthesis process, because we're able to automate and accelerate much of this process, as soon as you define the operation target, that's where the human designer comes in. You know what the targets are. I need this fast running on this, let's say ARM processor with this much memory on board, and I've got my collection in case. What I need to do just is kind of prototype what the model might look like. Doesn't have to be trained, doesn't be complete, and then GenSynth help takes over and does essentially all the exploration and optimization of your design through a combination of auto model generation as well as auto model explainability. So GenSynth then automatically creates a collection of models that all meet your functional requirements, but with different trade-offs that you as a designer can pick and choose. And you're also able to really understand their individual decision-making behavior so you can see which one matches your task and is essentially making the right decisions for the right reason. And so this whole iterative process kind of goes away and gets automated, allowing you to have something that's ready to deploy on your hardware with good accuracy and good efficiency. So hopefully that answers the question.
Yeah, let us know if it didn't. If you have any more follow-up or details you would like, please pop them in the Q&A and we can dive into it further. There's a couple other comments and questions that came in. So there's one that says, how is class and balance process handled at DarwinAI?
So I could go into more details. So as part of the DarwinAI genosynthesis technology, it has as I mentioned, it has the automatic ability to kind of understand your data as well as operational requirements to create new and improved models that are catered to your task and requirements like efficiency, accuracy at hand. And so as part of the process, there's a dynamic learning technology that's incorporated that will look at your data and identify the imbalances and then help train and build your model in a dynamic fashion so that it accounts for these imbalances, so that it performs in a much more trustworthy as well as fairer manner.
Mm-hmm. Makes sense. And then another question related, of course, to the data is how do you decide how much data needs to be labeled? And I guess that's just kind of a general question for, data modeling and, data labeling in general. But for your tools, what are you seeing as far as how you decide that with the customer?
So I could speak more to that after. I'll let Jake go first.
Oops, I was muted. Yeah, sorry, Alex. I'll hand it over here in a sec. I'd just like to bring up that we have worked with and currently work with some customers that have very limited amounts of data. That's a huge problem in the manufacturing space, because when you manufacture things, the amount of bad when I say bad images, I mean defective images, is very low, because if you're doing a good job as a manufacturer, you're building good products. So that brings into the reality that when you're training a model and you're looking for classification of defect 1 versus 2 versus 3 versus 4, you need to have samples of those images. So we resort to synthesized data, which hopefully Alex can talk to a little bit. That's how we try to supplement the model training process, given that problem.
Mm-hmm. So I'll add a bit more to that. So as I mentioned before, dealing with balances, we have essentially a dynamic learning approach to doing that. And as part of this dynamic learning approach, as Jake mentioned, we have proprietary synthesis techniques that will take even a small amount of data and be able to synthesize different types of scenarios that's catered to the task and requirement at hand, so that it's able to help compensate for that. That said, how do you actually know whether you have enough data, even when leveraging our synthesis tool? And that's where the explainability really comes into play. And because you have explainability and transparency throughout the entire process, what you're able to start seeing is that as you hit a certain level of sufficient data, leveraging our synthesis and so on and so forth, you'll start being able to see the actual decision-making behavior being a lot more logical and a lot more sound. Whereas if there's just way too little data, then what you'll see is that it starts overfitting, and from an explainability perspective, it no longer, you can see that the decisions or critical factors being used are no longer really generalizable. And so that's where the explainability in addition to these synthesis techniques that we have at DarwinAI really allows for this.
Great, great. Thank you. Well, hopefully that answered those questions that you guys had. I think we're pretty much we're getting to the 45-minute mark, so that is perfect timing. What I would like to say is if you have further questions, please feel free to reach out to DarwinAI directly. You can reach them via their website, or Jake and Alex, what's the best way? Is there a contact button on the new DarwinAI website that they should use to get some more discussions going?
Yep. So there should be on the website, but also have a look in the chat, because Brian, our director of marketing, just put in an email address there, and also a link to our contact us page.
Perfect. Yeah. So marketing@darwinai.com, or there's also a link in the chat, which is a direct link to the contact button. So, feel free to, explore more. DarwinAI is really impressive. I've really enjoyed watching them the last couple of years. They've been in our partner program, and we really love having them as part of the ecosystem. So don't be shy. Go talk to them. They have great technology. And then Jake, if you just go to the next slide before I let you go, we do have our Dev Summit coming up in October. So there's a call for papers open. So if you want to actually present, there's an opportunity, but also registration will be open soon. This is our flagship conference that you don't want to miss. So check that out at devsummit.arm.com. I think we are done. But thank you very much for attending. I hope that you found this useful. Please fill out the survey. Again, like I said, we want to bring you the content and the topics that you are interested in. So please let us know how we're doing. And you might get a Arduino BLE33 board for your efforts. They're pretty fun. You can make a lot of cool things with them. So anyway, thanks, Jake and Alex, for your time. And thank you, everybody, for being with us today. And we'll see you next time. Have a great one. Bye.